In section 1.5, we're going to look at something called uncertainty in measurement. In the previous section, 1.4, we talked a little bit about the idea of measurement from the perspective of measuring physical and chemical properties. Now we're going to look at a little bit more of the arithmetic for uncertainty. So when we make measurements, we generally think of measurements as having two properties. One is a number, a value, and the other one is the unit. For example, we could measure how fast an airliner is flying across the country, and we might find that it's flying at 475 miles per hour. So 475 would be the numerical value of that measurement, and then miles per hour would be the units for that. In chemistry, we often measure things like density, which is something that has a number associated with it, and then units associated with it. So we're going to take a look at how we deal with what's called uncertainty. And the issue here is that we need to be able to have some confidence that the number that we're reporting is an accurate measure of how well we understand something. So for example, if I said, look into a football stadium and look around and see how many people in there, and I were to say, okay, in that stadium, it looks to me as though there's 47,333 people. Well, that's an interesting number to report, because how would I be able to know just by looking at that many people that there's all the way down to the individual person? Now, if I were to say, it looks to me like it's about 47,000, then maybe people would say, yeah, that's, you're estimating that. So the issue here is how many digits can we have confidence in how we report our measurements? Is there 47,000 or is there 47,333 people in that stadium? We would say that if we report that the number of people is 47,333, that there's greater precision or less uncertainty than if we said 47,000. 47,000 would have more uncertainty and less precision. Okay. So let's take a look at a couple of definitions here. One is that an inch is defined as 2.54 centimeters. A kilogram is defined as 1,000 grams. 12 is a definition of a dozen. These are what we would call exact numbers, meaning they're defined in a specific way. We are, by agreement, claiming that 12 is a dozen, not 12.5, not 13, not 11, but exactly 12. That's called an exact number. The same is true for an inch. An inch is defined as 2.54 centimeters. So those are called exact numbers. Another example of exact numbers are counting. So for example, if I counted the number of people in a classroom and I came out with 16, we will assume that if that number is relatively small, unlike a large stadium full of 47,000 people, that a small number, a reasonably small number, is an exact number. Now, it is true, I could be wrong, I could miscount, but we'll assume that my counting procedure is correct, and I count 23 people, that would be an exact number. But there are other types of numbers which are considered inexact, meaning they're not necessarily the number exactly as I'm reporting. So for example, if I say that an airliner is flying at 475 miles per hour, we recognize that that's probably subject to change, right? It's probably going to vary a little bit. Furthermore, that number that we're reporting is sort of based on some form of measurement of perhaps radar bouncing off the airplane and figuring out how far it's flying over a given amount of time, or some device within the instrument, or perhaps GPS, some way of telling how fast it's going, and that's not an exact number. Now, it might be very, very, very accurate. Maybe it really is 475, but it's probably not 475.0000 miles per hour, not exactly 475. In a sense, exact would be 475.0 with an infinite number of zeros. Like we know it exactly out as far as you want to measure. So those are inexact numbers. An example of that would also be my weight. Yeah, I probably weigh 170 pounds today, but is it exactly 170 pounds? It depends on how good my scale is. Another scale might say it's 175.2. A better scale might say 175.3. So 175 is not an exact number. It's a measurement that I'm making that is subject to some variation. Okay. Now, let's talk about how we discuss this issue of exact versus inexact. If we're dealing with an inexact measurement, like my weight or the speed of an airplane, we report what are called significant figures. A significant figure, as it states here, is reported to be a meaningful digit in a reported number. So a digit, a number that has some meaning to it. So they give an example here of looks like a flash card here, a 64 gigabyte flash card, and someone is measuring the width of that flash card. In the top, there's a centimeter scale, and if you take a look at the centimeter scale, it looks like it's just marked off as individual centimeters, 1 centimeter, 2 centimeters, 3. And so if we were to measure how wide that is, in fact, this is often what they do with children in the first or second grade. They would give them a little centimeter stick like this, and they'd say, measure it. And they would say, oh, it's 2 centimeters. But down below, we might do this measurement with some older children and ask them to report it to more significant figures. So we might say, oh, well, it looks to me as though it's more than 2 centimeters. In fact, it's about 2.4 centimeters. So they would report it with 2 significant figures. In fact, if they're even really, really clever about it, close one eye and look in there really closely, it looks like it's halfway between the 4th line after the 2 and the 5th line after the 2. So maybe that's 2.45 centimeters, halfway between 2.4 and 2.5. So that would be 3 significant figures. So the meaningful digits for the top would just be 2 centimeters. But on the bottom, there might be 3 meaningful digits, 2.45. That's 3 significant figures. If we reported it as 2.5 centimeters, then that would just be 2 significant figures, or significant digits, if you want to use that terminology. So it depends. The width of that flash card, of the memory card, depends on what type of ruler we're using to measure it. But the number, counting the number of significant figures, is something that we will do. So here are some rules about significant figures right here. It says rule number 1 is that any digit that is not 0 is definitely significant, no exceptions. So if you look at the number 112.1, every digit in there is non-zero, the 1, the 1, the 2, and 1. So that's 4 significant figures. Each digit is significant. It gets more complicated if we're dealing with zeros, and there's a little bit of controversy over how we deal with zeros. One is, point 2, zeros located between non-zero digits are significant. So 305, the 0 is between significant or non-zero digits. The 0 is between a 3 and a 5. So those are significant. So that 0 would be significant. And so that number, 305, would have 3 significant figures. So 3, 0, and 5. Another example, 50.08. Both of the zeros are between numbers that are not 0, the 5 and the 8. So they would both count as significant. So 5008, all 4 would be considered significant. So that's 4 significant figures for that one. Okay, that's not too bad. Then you look at rule 3. Rules to the left of the first non-zero digit are not significant, and it doesn't give you any exceptions here. So if you look at the number 0.0023, the non-zero digits start with the 2. So every 0 before the 2 is not significant. So all 3 of those zeros are not significant. So only the 2 and the 3 are significant. So that's 2 significant figures. If you look at the number 0.000001, all the zeros are to the left of the non-zero. So they are not significant. So only the 1 is significant. So that number only has one significant figure. So counting sig figs, we say, counting the number of significant figures is a skill you want to develop with some of these practice problems. Let's look at rule number 4. Zeros to the right of the last non-zero digit are significant if the number contains a decimal point. Okay, so for example, 1.200. If the number has a decimal point, this one does, those are significant to the right of the non-zero. So the zeros to the right of the 2, because the number has a decimal point, they are significant. So that's 4 significant figures for that one. Be careful if you're from a country other than the United States where you use the decimal to indicate powers of 10 and the comma to indicate decimal points. In the United States, we use the dot, which looks like a period, to indicate a decimal point, and we use commas to indicate powers of 10, like 1,000, a million, a billion. So try to use the same notation that we're using in here. Number 5, the last one, and this one is a lengthier one. Take a look at that. There's as much writing with number 5 as there is with the first 4 altogether. Zeros to the right of the last non-zero digit in a number that does not contain a decimal point may or may not be significant. Okay. 100, for example, might have 1, 2, or 3. It's impossible to tell without additional information. In other words, if the zeros are to the right and there's no decimal point, we don't know whether they're significant. That's interesting, right? So there are ways to figure it out for many examples, and we'll perhaps go with that later on in this question, in this number 5. To avoid ambiguity in such cases, it's best to express such numbers using scientific notation. By the way, scientific notation is discussed in Appendix 1, and I will have a video on scientific notation. I'll post that at some point. But if you want to look ahead to Appendix 1, it'll talk about scientific notation. If the intended number of significant figures is 1, the number is written as 1 times 10 to the 2. So you take that number, 1 times 10 to the 2 has one significant figure, because there's only one number there. So that'd be 100. But if you want to have 2 significant figures, you would write 1.0, and that gets you back to rule number 4. If there's a decimal point, the 0 to the right of the non-zero counts. So 1.0, that 0 would count, so you'd have 2 sig figs. If you want all 3 to count, then you would write 1.00 times 10 to the 2. And then again, according to rule 4, the zeros to the right of the non-zero would count as significant figures, and you'd have 3 sig figs. So 1, 2, 3. So let's take a look at sample problem 1.5. Determine the number of significant figures in the following measurements. A, 443 centimeters. Well, for A, all 3 of those digits are non-zeros, so they all count. So that's got 3 sig figs. B, 15.03 grams. Well, there's a 0 in there. That 0 is in between non-zeros, so that counts. That would be rule number 2. So that's 4 sig figs. In C, there's 2 zeros. Those are to the left of the non-zeros, so they do not count according to rule 3. So only the 3, 5, 6 counts, so that's got 3 sig figs. D, 3.000 times 10 to the minus 7. So notice they're using the scientific notation in order to tell us how many sig figs, because the zeros are to the right of the decimal point. If they are to the right of the decimal point, they count, so 3.0004 sig figs. 50 centimeters, ambiguous, 50, we don't know, right? There's no decimal point in there, there's no scientific notation, so it could be 1 if it's just the 5, or it could be 2 if the 0 counts. F, 0.9550, the 0 on the left doesn't count because that's to the left of the decimal, or that's to the left of the non-zero. The 0 on the right, well, there is a decimal point. If there is a decimal point, then you go to rule number 4. If there's a decimal point, 0 to the right counts. So 4 sig figs. And so there you go. So that's sample problem 5, 1.5. You can try the practice problem A and B, and that'll give you an idea there. Now, the next step, after we count sig figs in numbers, is we do calculations with them. And there are two types of calculations we have to learn. One is addition, subtraction, adding and subtracting, and the second one is multiplying and dividing. So let's do the adding and subtracting first. Now, point number 1 here. In addition and subtraction, the answer cannot have more digits to the right of the decimal point than the original number with the smallest number of digits to the right of the decimal point. I know this sounds a little confusing, but it's very difficult to put ideas into language and to also make it seem very simple. So let's take a look. Suppose we're going to add these two numbers, 102.50 and 0.231. Well, what you do when you add is you line the numbers up so that the decimal points are in the same column. And then you count how many digits after the decimal point each number, each measurement has. The first number goes 2 digits past the decimal point. Now, that second digit past the decimal point is a 0, but remember, go back to our rules. If there's a decimal point in the measurement, zeros at the end do count. So that 0 counts as a sig fig. If we look at the second number, 0.231, that goes 3 digits past the decimal point. So here's what you do. You add the two numbers, include all the numbers. So if you add those two together, you get 102.731. Now you ask, how far to the right of the decimal point are we justified in reporting our answer? We cannot go more digits to the right of the decimal point than the one that goes the fewest. Can't go more than the one that has the fewest. The 102.50 only goes 2 digits past the decimal point, so we can't go more than 2. So here's what we do. We take our 102.731 and we round it. We round it to the second digit past the decimal point. And in the rounding, the second digit is a 3 past the decimal point. The number that comes after that is less than 5, so we just truncate it. We get rid of the 1. So now the answer would be 102.73. That would only go 2 digits past the decimal point. Okay? Let's look at another example. 143.29 minus 20.1. The second number goes 1 digit past the decimal point. So our answer can only go 1 digit past the decimal point. So what you do is you line them up, you do the arithmetic. Don't get rid of any numbers yet. Don't round it yet. Just do 143.29 minus 20.1. That gives you 123.19. Then you go back and you look. The one that goes the fewest digits past the decimal point is the 20.1. That goes 1 digit past the decimal point. So our answer has to go 1 digit past the decimal point. So you say, okay, 123.19, we're going to round it to 1 digit past the decimal point. Well, 19 gets rounded up to 2. 19 gets rounded up to 2. So 123.2 goes 1 digit past the decimal point. Okay? Multiplication division is a different rule. It's the same idea. The principle behind all of this is we can't have an answer that has more precision than any of the measurements we made. So if you make multiple measurements, you can't have an answer that's known better than the worst of the measurements that you made. So an example is 1.4 times 8.011. Well, in multiplication division, it's actually simpler than it is in addition subtraction. The answer gets rounded to a number that has the same number of sig figs as the measurement that has the fewest. Let me say that again. The answer gets rounded to a number that has the same number of significant figures as the measurement that has the fewest number of sig figs. So in those two measurements, 1.4 and 8.011, the 1.4 has the fewest number of sig figs, only 2. So our answer can only have 2. So we do the calculation, 11.2154, but we round it to 2 sig figs. And if you round it to 2 sig figs, 11 would be your answer. Okay. Second one, division. Same rule. You do the operation, in this case division, and then round it to the number of sig figs as the measurement that has the fewest. Out of those two measurements, 11.57 and 305.88, The first one, the one in the numerator, 11.57, has the fewest number of sig figs, 4. So our answer gets rounded to 4 sig figs. Now this one's a little trickier because it's a decimal number. If you run it through your calculator, you'll get 0.037825 all the way out to a 4. If you round it to 4 sig figs, remember that 0 to the left doesn't count. Zeros to the left of the non-zeros never count. So both those zeros on the left don't count. The 3 that counts, the 7 counts, the 8 counts. The next digit is a 2. The number that comes after it is a 5 or greater, so it gets rounded up to a 3. So 0.03783 has 4 sig figs. That's limited by the measurement 11.57. Now, what about exact numbers? It says here in point 3, exact numbers can be considered to have an infinite number of sig figs. So if you have if you have 3 pennies, for example, and each penny weighs 2.5 grams, and you want to know what the total mass is, we wouldn't say, oh, you have 3 pennies, that's only 1 sig fig. We would say the number of pennies is an exact number, so it has an infinite number of sig figs. The 2.5 grams, that's the measurement, that has 2 sig figs, so our answer would be 7.5 grams. So the mass is not an exact number, 7.5, but it's limited by the mass of 1 penny in terms of its number of sig figs. What do you do if you have multiple steps? Well, one piece of advice, and it talks about it a little bit here, is don't round it after each step. Don't round it till the end. The last step, round it. And the reason is if you keep rounding step after step after step, even if you just have 2 steps, some types of problems you have 3, 4, 5 steps. If you round it after each step, you will bias the final answer to being smaller than it should be. And that's called rounding error. So in the first step, do the calculation, keep all the digits, do the second calculation, keep all the digits, and then go back and look at your data, figure out how many sig figs were in there, and then round it at the end. Okay? So let's take a look at sample problem 1.6. Perform the following arithmetic operations and report the result to the proper number of sig figs. A, 317.5 milliliters plus 0.675 millimeters. So notice that's addition or subtraction. So the rule there is the answer cannot have more digits past the decimal point, to the right of the decimal point, than the one that has the fewest. The 317.5 milliliters only goes 1 digit, whereas the 0.675 goes 3 digits past the decimal point. So you got to round that so that there's only 1 digit past the decimal point. It's limited by the 0.5. In part B, 47.80 minus 2.075, 0.80, that goes 2 digits past the decimal point. Remember, the 0 counts because there's a decimal point. If it's to the right of the decimal point, it does count. So it goes 2 digits. 2.075 goes 3 digits past the decimal point. So our answer can only go 2 digits past the decimal point. In part C, now we're doing division. Now we just count how many sig figs there are. So you would do the calculation, get a number, round it to how many sig figs? Well, 13.5 has 3, 45.18 has 4. You pick the fewer 3, so round it to 3 sig figs. In D, we're doing multiplication, same as division. The first measurement, 6.25 centimeters, has 3 sig figs. The second measurement, 1.175 centimeters, has 4 sig figs. Rounded to 3 sig figs, the fewer of the 2. And then finally, in E, it looks like addition, although it's complicated here, right? 5.46 times 10 to the 2 grams. How many sig figs does that have? 3. 4.991 times 10 to 3 grams. How many does that have? 4. But we're doing addition subtraction. So for E, we have to be very careful. Generally, what we would recommend is that you change the exponent in one of them so that it's the same as in the other. So the first number is 10 to the 2 and the second is 10 to the 3. Make them both 10 to the 3 or make them both 10 to the 2. I'm going to scroll down to the solution for that one. If you take a look in part E, what they did, they changed the second number to be 10 to the 2. Once they're in the same exponent, then you can line the numbers up for addition subtraction. And so take a look. They're both times 10 to the 2. They both go 2 digits past the decimal point. So that means your answer is going to be 2 digits past the decimal point. So 55.37 times 10 2 grams. But what they did was they did something interesting. They changed it back to 10 to the 3. Again, that's an issue with scientific notation. Scientific notation is a number between 1 and 9, or 1 and 10 actually, times 10 to some value, to a whole number. So 55.37 is not a number between 1 and 10, it's a number greater than 10. So they changed it to 5.537 times 10 to the 3 instead of 10 to the 2. Try practice problem A, B, and C. Sample problem 1.7 is an issue where you're calculating the density. If you recall from previous section, density is mass divided by volume. So you're doing division, mass over volume. But they're also doing an issue here where they're making two mass measurements. And the mass of the gas is actually the difference in those two masses. So they're also doing subtraction. So this one is interesting. So take a look at the solution here. First, you find the mass of the gas. So the idea here is you have a container. If it's empty, it weighs 124.6 grams. If you put the gas in, it weighs 126.5. So it went up because the gas has a mass. What's the mass of the gas? The difference between those two values. So if we do the subtraction, 126.5 grams minus 124.6 grams, that's a difference of 1.9 grams, 1 digit past the decimal point. So that right there is the mass of the gas. The volume is given as 9.850 times 10 to the 2 centimeters cubed. That has 4 sig figs. Remember, the 0 counts because it's to the right of a decimal point. So you take the mass divided by the volume, 1.9 grams over 9.850 times 10 to the 2 centimeters cubed. You get an answer, 0.000193 grams per centimeter cubed. How do we round it? Well, it was 1.9 grams. That was pretty straightforward. But now we do division. There's 2 sig figs in the numerator, 1.9, 4 sig figs in the denominator, 98.50. So the answer should have 2 sig figs. Remember, with multiplication division, it's going to have the same number of sig figs as the measurement that has the fewest. So that would be 2. So they're rounding it to 0.00193. So they get rid of, 19. They get rid of the 3 at the end because that would be 3 sig figs. Again, remember, zeros to the left of non-zeros do not count ever. So there's one that's a multiple step. You're doing subtraction, then you're doing division, 2 steps. There's your analysis. Try practice problem A and B. And then there is a discussion of accuracy and precision. Just briefly, what is accuracy and precision? Accuracy is how close to an actual value you are. So here is an analogy. Imagine that you throw a bunch of wadded up papers into a basket, and they all go in. We would all understand that, hey, you were being pretty accurate. You're putting all the wads of paper, throwing them into the basket. That's high accuracy. If you throw them and they're all pretty close, that would be, less accurate, but somewhat accurate. If they're far away, that would be inaccurate, very inaccurate. But there's also an issue of precision, which is how close are the tosses to each other. So imagine you throw them all, but they're all the same distance away. They're all close to each other, but far away from the basket. We would say that you weren't very accurate. You didn't get them very close to the basket, but you threw them to the same spot. That would be called high precision. So the closer they are to each other, so each paper wad, the higher the precision. The closer they are to the basket, the higher the accuracy. So in C, picture C, they're all away from the basket, so no accuracy, or very little accuracy, but they're also far from each other, so you were not very precise as well. So far from each other, low precision. So this comes up as an issue because sometimes we make multiple measurements of the same thing. if you send a medical sample, like a blood test, to the lab, they might only measure it once, but they might measure it 2 or 3 times and just see if they get the same answer. So imagine that 3 students are making some measurement. It's not telling you what they are here, but they're making 3 measurements. Student A measures something as 0.335. They do it again, they get 0.331. And they do it again, and they get 0.333. Student B does it as well and gets 357, then 375, and then 0.338. The averages are calculated at the bottom there. And then student C gets 0.369, 0.373, and 0.371. We could look at accuracy and precision, and one way to look at that is to graph it. So if you look at the graph in this figure 1.13, student A had 3 measurements very, very close to each other. They're down at the bottom in yellow. Really close, but they're very far away from the actual value, 0.370, the true value of the mass of the tablet. So we would say very high precision, very precise measurements. They're close to each other, but not very accurate. They're pretty far from the actual value at 0.370. Student B, well, it looks like one of the measurements was pretty close to the true value, 0.370, but the other 2 were pretty far away, so not that accurate. Maybe a little better accuracy than the first student, but very poor precision, right? Because the 3 measurements of student B are all over the place, not close to each other at all. So maybe a little better accuracy than student A, but much worse precision. Student C. All 3 of the measurements are right on top. They're very, very close to the true value at 0.370. So they're close. In fact, the average was 0.371. That's really close to the true value, 0.37. So that's high accuracy, but each measurement is close to each other. So that's also high precision. So again, high accuracy is essentially the average value. Is that close to the true value, the accepted value? High precision are the values you measured multiple times close to each other? And that would be high precision. So you can also take a look at these checkpoints. There's 4 of these checkpoints to take a look at those ideas of accuracy, precision, counting number of sig figs, and figuring out how many sig figs an answer of a calculation would have. And that would be pretty much a good wrap-up for section 1.5, uncertainty in measurement. The next section, we're going to take a look at a little bit more details at calculations in chemistry in a general way.